Hello, and welcome to CSM Week 7, Question 3, Degenerate. The question says, consider the operation of adding elements to a binary search tree. Given two sequences of numbers, sequence A, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, sequence B, 4, 2, 6, 1, 3, 5, 7. Insert the numbers from each sequence into empty BSTs. Describe and compare the resulting trees. And then they give us these two generalizations of what sequence A does and what sequence B does in terms of how the elements are going to be added into these two separate BSTs. Before this, I want to give a super quick summary of what a binary search tree does and how you can add elements and search for elements in a binary search tree. A binary search tree is comprised of nodes in which every node always has two children. And the nodes, for example, this top value right here is x, and this value is y and z. All the values to the left of x are going to be less than x, so that means that y is less than x. And all the values to the right of x are going to be greater than x. That means that z must be greater than x. And so then following this rule of adding values into a binary search tree, let's look at what sequence A is trying to tell us. It says that for sequence A, we are adding values from 1, 2, 3, up until n. Now what this means is that every single value or every single new node you add to this binary search tree, every single n plus 1 node is going to be more than every n node. What I mean by that is that, for example, I'm going to zoom in here. For example, in this case, after you add element 1 into your binary search tree, the next element 2 is always going to be more than 1. And then 3 is always going to be more than 2, and then so on and so forth until we get a sequence of up until n values. Now, how does that look like as an actual binary search tree? So I'm going to section this off. Sequence A and sequence B. Well, following the rules that I mentioned above about how to add values into a binary search tree, we know that after you add element, 1 in this top case over here, you add element 1, and since 2 is more than 1, you add it as a right node from 1. Then after you add element 3, 3 is more than both 1 and 2, so it becomes a right leaf of node 2. And this follows a similar pattern all the way until you reach node 7. And this binary search tree is called a degenerate because because first of all, it's not balanced. And for a binary search tree to be balanced, every single node must have two children. So in this case right here, this binary search tree is balanced because the node x has two children, y and z. But in this case right here, this binary search tree is not balanced because every node does not have two children. In this case, this example is the degenerate, in which it's not balanced. Oh, I misspoke. This is not balanced. Okay. Now I want to draw out what sequence B, after adding values, what the binary search tree is going to look like after adding those values for sequence B. Okay, sequence B says, right here, it says, a sequence of n numbers inserted such that they create a balanced binary search tree. Now, these properties of a balanced binary search tree are what I mentioned before, such that every single node, I'm just going to write this down. Every node has two children, okay, and all values less than the node go on the left, And the same thing, I'm just gonna put quotation marks here, but greater than go on the right. Now following these rules, let's go back to sequence B here, look at sequence B, and now create this now balanced binary search tree. So the first node that we have to add is 4. So we add 4 as this root node. Then we are looking at element 2, and because 2 is less than 4, it is going to come as a left child of 4. Okay, now the next element we have to add is 6. 6 is greater than 4, so then you're going to add this node as a right child of 4, and so on and so forth. So in this case for 1 is less than 4, but it's also less than 2. So it acts as a left child of 2. 3 is less than 4, but greater than 2. So it becomes a right child of 2. And then 5 is greater than 4, but less than 6. So it becomes a left child of 6. And then last but not least, we have 7, which is greater than 4 and greater than 6. So it becomes a right child of 6. And therefore, sequence B creates a balanced binary search tree and follows this property that I mentioned before. Okay, now let's look at this next question, 3.4 right here. What is the runtime to insert the n elements for each BSD? What about searching for an element? Okay, I'm going to break this up into, once again, sequence A and sequence B. Sequence A and sequence B. And when talking about runtime, I always have this convention that has always helped me when finding the right runtime for asymptotics is that you want to find the runtime of one operation and multiply it by the total number of operations happening in that given given question. And this convention is almost always going to give you the correct runtime for each given scenario. So when talking about inserting elements for sequence A, okay, we're talking about inserting elements for sequence A. And once again, this convention that I have up here is for insertion, not for searching. Okay, so for insertion, what's the runtime of one operation for sequence A? Runtime of one operation. Well, given this above diagram that I have here of sequence A, if we were to add a new element to this binary search tree, we're going to have to go through all the elements that are already in this tree to add the next element. So for example, if I were to add an element or a node 8, so let's say I add a node 8 to this, to sequence A's binary search tree, I'm going to have to go through all of the elements of this binary search tree to then finally add 8 as the leaf or as a right child of 7. And because of that, we are going through by adding one node, it takes n time because adding a new node to this binary search tree depends on the length of the number of elements of this binary search tree. So therefore, the runtime of one operation is omega of n. But because we want to insert n elements, the total operations is n. And if you multiply these two together, the total runtime becomes omega of n squared. And this is your answer for the insertion of sequence A. Now let's go into searching. And for searching, you're always going to want to analyze two case scenarios. The best case, and the worst case scenario. Okay. Well, going back to our diagram above, the best case scenario is that the element that we want is the first node of our binary search tree. So in that case, for example, if we want this element 1, well, this is only going to take omega of 1 time, right? Because we're not going to go through all the values in this binary search tree because all that we want is just the first element of this tree. So in that case, the best case scenario is going to be omega of 1. Now, the worst case scenario is different because let's say we want this value 8, right, in this given tree. We're going to have to go through all the elements of this binary search tree to actually find this value of 8. And therefore, because there's always going to be n elements or n nodes in this binary search tree, the worst case scenario to find this last node in this tree is going to be omega of n. Okay. Now let's go over sequence B with taking a look at this image that we have right above it. Okay, so this is now going back to insertion for sequence B. Now sequence B is a proper binary search tree, okay? And let's say we want to add a value to this binary search tree. Well, what's the runtime of one operation? Runtime of one operation, right? Well, because we have n elements in our binary search tree, it's gonna runtime of one operation is gonna take omega of n. Okay. Now, because our binary search tree, and I make this make a note of this because this property is really important to know for binary search trees. The height of a binary search tree is always going to be log of n. So for example, if I have a tree that looks like this, that has, you know, two nodes per parent, and this goes on, you know, up until n, the height of this binary search tree is going to be log base 2 of n because there's 2 children per parent. But in asymptotic notation and in this arithmetic, you don't really care about this base, log base 2. So the height of this binary search tree is going to be log base of n. Okay? That means for any BST, the height is always going to be log of n. So therefore, the total number of operations is going to be omega of log of n, which means if you multiply these two together, the runtime becomes omega, oh, not omega equals 2, but omega of n log n. And this is your insertion runtime. Okay, now let's go over searching. And once again, we have to analyze two components, the best case scenario and the worst case scenario. Similar as, you know, the sequence B's best case scenario, if, for example, if the element that we want is the root node of your BST, for example, if we want 4 from this BST, well, because this element is the first, it's like the first element in this BST, it's not going to take at all, if anything, much time to retrieve this element from the BST. Therefore, this runtime for the best case scenario is going to be omega of 1. And the best case, once again, to repeat, is when the element that you want is the first or the root node of your BST. Okay, now what's the worst case scenario? Well, this worst case scenario, for example, is when you want to find a node or element that's on the last layer of your BST. For example, we want to find this element 7. in this BST, okay? It means that we need to go through all the values within this BST until we find, oh, a 7 that we actually want to search for. And so in that case, we're going through the height of this BST. And once again, the height of a BST is always going to be log of n. So the worst case scenario is going to be omega log of n. And these are both the answers to this question. And this also concludes question 3, degenerate.